This, this slide shows the outline of my talk consists of 5 parts. First of all, I will explain the background to this work, briefly reviewing some related researches. Next, I explain our target system and its job scheduling. Then, I will discuss the job scheduler simulator development and show you the validation result of our job scheduling. I'll discuss the use cases we envision for the digital twin. Finally, I'll summarize my talk. First, let us describe our research background. HPC systems are used not only for traditional simulation, but also the AI-PD domain. The computational demands are expanded day by day. HPC systems are evolving to meet this demand and various user requirements. HPC systems are becoming more heterogeneous, larger scale, and more complex, and the user community is expanding. So HPC system administrators are required to maximize the value of the HPC system while satisfying these user demands under limited computing resource and power. The HPC system administrators use a job scheduler to schedule jobs to computing resource to the system. Backfill scheduling is a typical job scheduling algorithm that has some parameters to efficiently use idle computing resources. Another example is multi-queue scheduling that define a queue for each job priority and enable urgent job operations. The system administrator can associate each job queue with computing resources. If certain queue is congested, the system administrator changes the resource balance among the multiple queues so as to reduce the queue congestion. Power saving scheduling reduces idle power by shutting down a node when it has not been used a long time by using a threshold to judge if the node should be turned off. In this way, the system administrator combines several job scheduling ideas and mechanisms to operate the HPC system. As a result, they need to adjust so many parameters to operate the system. One important point is it requires expert knowledge and deep understanding about system configuration to estimate appropriate parameter values. Since the system is in operation, they cannot easily change the parameter configuration. So when they change the parameter configuration, they need to carefully consider if the new parameter configuration will improve the system operation for sure. So the final goal of this work is to build a digital twin of an HPC system to reduce the burden on the administrators. This is an overview of the system purpose in this work, proposed in this work. The left figure is an HPC system in operation. There are a lot of operational data such as CPU usage, workload information, job scheduling information. The middle figure is the system administrators. They monitor the HPC system. The right figure is a virtual HPC system on a small computer. It reproduces using operational data. This virtual HPC system is a digital twin for HPC system. Using a digital twin, the system administrator can run various simulations of the virtual HPC system. Then, based on the simulation result, they find the optimal operation parameters and apply them to the actual system. We believe that repeating this cycle reduces the burden on the administrator and maximizes the value of the HPC system. Let's briefly review some related studies. Recently, many researchers have focused on AI-based job scheduling. but it will not replace the conventional job scheduling very soon. So human system administrators manually need to monitor and just adjust system parameters to maximize the resource usage and throughput. Next, this slide summarizes related studies on job scheduling simulators. The job scheduling simulator is a core component, is building a digital twin of job scheduling. Many studies have been conducted on this topic for a long time. Arena, grid sim, and bat sim are widely used for various purposes in job scheduling research, such as for making a comparison among the scheduling algorithms. But they do not intend to simulate a particular system. Recently, SLAM simulator has been introduced for simulating a real-world HPC system. SLAM simulator has been developed using the SLAM code and can reproduce the behavior of SLAM well. It is very useful for SLAM users, but it can, of course, simulate only SLAM job scheduling and not other job schedulers. As the first step of building a digital twin of an HP system, we focused on reproducing job scheduler of a real-world system. To this end, we extended the SLAM simulator to be able to implement the scheduling algorithm of another scheduler named NQSV. Then we demonstrated that a digital twin on our HPC system enabled to examine parameter configurations without distributing the system operation. Now, let me explain our target system and its operation. Our target system is named AOBA-A, which is installed at Tohoku University. AOBA-A consists of two subsystems. One is a vector cluster called AOBA-A. The cluster consists of 72 nodes of NEC XX Aura Tsubasa. Each node of SX Tsubasa is equipped one AMD and 8 vector engine. NEC vector engine has NEC vector processor and HBM modules. The other is a Scala cluster powered by AMD EPIC. Our focus is on this powerful vector cluster of AOBA-A. Next, I will explain the AOBA-A's operation and queue settings used in practice. AOBA-A provides 4 types of usage. There are free use, paid use, reserved for specific users, and urgent jobs. In free use and paid use, the nodes are shared by many users. In addition, there are multiple queues according to job size. 4 nodes are dedicated to the free use of executing only very small jobs. 58 nodes are allocated for small, medium, and large jobs. If a queue is congested, the system administrator adjusts the resource balance of 6 nodes between free use and paid use to reduce queue congestion. AOBA uses NEC proprietary job scheduler named Network Queuing System B. There is some parameters used in AOBA's operation. You can see that there are a lot of parameters. The system administrator determines most of these parameters at the time of this system design. That is, parameter value has been decided before the actual system operation. After starting the system operation, changing parameter just for validation is not allowed in general. Therefore, there is a demand for our job scheduling simulation to make sure that the parameter configuration is adequate for the actual operation. Next, I'll describe the AOBA-A job scheduling simulation. Since AOBA uses NQSP, our scheduling cannot be reproduced by the existing job scheduler simulator. Then, we decide to extend SLAM simulator to reproduce NQSP job scheduling. SLAM simulator has a mechanism to use custom plugin to implement an extended feature, which is not provided by the original SLAM simulator. We took advantage of this mechanism and developed an NQSP plugin. And the plugin includes a translator module that converts the difference between SLAM and NQSP. For example, translator converts resource usage limitations decided by SLAM at job submission to another data format using NQSP. In addition, SLAM simulator cannot simulate how long it takes to start up and shut down node, which is a timing overhead of node power management. In order to reproduce this behavior, we added a node state simulator to simulate the timing overheads. In this work, we experimentally discuss how the simulation can help the system operation. All job queues in the simulation are empty at the beginning. So we use the 10,000 job records since the system maintenance in April 2021. By using this job data set, the initial status of each job queue in the simulation is the same as that in the observation. The figure shows the difference between the simulation results and the actual observed data. The left figure shows the histogram categorizing the difference of job start times. For example, -6H means that a job in simulation has started 6 hours earlier than the actual job. The vertical axis shows the frequency of job each in category. You can see that about 6% of the job start time is accurately reproduced with the error of less than 1 minute. The right figure shows the difference in utilization. There is no difference at the beginning, but you can see that the difference is expanding more and more over time. This slide shows such a feature not implemented in the simulator. In reality, AOBA-A operates a periodic job submission operation. The operation uses a function of the NQSP job scheduler that specifies when to start a job. So the simulation result will be more accurate if the function is simulated. However, the use of this function is not recorded in job data. So we collected the data so that a job using the function is considered as if it submit at scheduled start time. The lower figure on this slide shows the simulation result with the data modification. You can see that the number of jobs with extremely large errors is obviously decreased. Based on these results, we think that implementing this NQSP function can further improve the simulation accuracy. We have so far shown that the simulator can reproduce job schedules with acceptable errors. Next, I will discuss how the simulation can help system operation. This slide shows job trace data observed at AOBA-A in April and May 2021. The horizontal axis shows the job submission time, which is indicated when the job was submitted. The vertical axis is the job execution time, which indicates how long the job was running. The size of each circle is the size of the job, which indicates how much computing resource was spent for execution. The color of each circle is the queue to which the job was submitted. One point in this chart is that the trend of job submission in April are different from those in late May. For example, in late May, green jobs continuously submitted. We conducted a parameter survey for each of these two patterns. The job submission pattern in April and May are called off period and busy period respectively. First, we discuss the job trace in off period. In the off period, we discuss how much the power management can save the power. Then, we discuss if the current parameter configuration is appropriate. The left figure shows the adjustable parameters of NQSV parameters power saving features. The right table is the list of the parameter configurations we simulate in this evaluation. Setting AOBA means the current parameter configurations of AOBA. Setting A is a case of power saving feature is disabled. If a node is idle for a long time, the node is turned off. The minimum idle time is a threshold to decide if a node is turned off. Setting B and C are the cases. The minimum idle time parameter is set to smaller and larger respectively. Setting D is the case to change the maximum number of turning off each node per day. A node is turned off if the node is estimated to remain idle longer than a certain threshold. Setting E and F are the cases the estimated idle time is set to smaller and larger respectively. Here is the result of the simulation. The line shows energy consumption. The bar shows the average waiting time of each case. In case A, energy consumption has increased, and the average waiting time has reduced a little. This result gives the administrator an idea of the effect of enabling the power saving feature. In case B and C, power consumption has changed a little, but the average time has not changed much. You can see that more aggressive power saving can save more power. In case D and E and F, power consumption did not change. You can see that there is no effect of changing parameter in this job pattern. Thus, using this simulator, you can see the effect of enabling power saving and changing parameters. Let us discuss the effect of power saving in busy period. The left figure focus on the job trace in 2 days, the busy period. You can see that there are continuous job submission and various job submission. The right figure shows the changes in the number of waiting job and running job when the simulation is run using this job trace. The x-axis shows time. The y-axis shows the number of jobs. Red line indicates the number of running jobs. A green line indicates the number of waiting jobs. You can see that the number of waiting jobs includes around 3 p.m. on May 28. In this situation, the system administrator should change the resource balance among the queue to reduce number of waiting jobs. The queue to reduce the number of waiting jobs. How the system administrators change the resource balance would be decided based on their experience and institution. So we ran a simulation on this case. The left figure shows the cases we change the resource balance among the job queues. We simulated 5 cases. In case 1 and 2, the node assigned to very small jobs is reassigned for other queues. In case 3 and 4 shows the waiting. In case 3 and 4, all job queues share some of the nodes. In case 5, all nodes are shared by all queues. The right figure shows the waiting time and energy consumption for each case. Case 1 and 2 and 5, you can see that the waiting time is reduced. Case 3 and 4, there is no effect of changing the setting on the waiting time. In all cases, there is no effect on power consumption. In the next, we will further discuss the effect of more aggressive power saving in case 2. This is to clarify how parameter tuning combined with resource balancing can change the waiting time and power consumption. This slide shows the simulation result. The left figure shows the changes in the number of waiting and running jobs. You can see that the number of waiting jobs has decreased due to the change in resource balance. The right figure shows the changes in the number of power off and running nodes. The upper right figure shows the simulation results before changing the configuration. You can see that when more aggressive power saving is applied, more nodes are turned off longer. You can also see that the number of waiting jobs decreases quickly, while the power saving time is increased. Thus, better operation can be achieved by customizing the resource balance and power saving parameters for this particular job sequence. Such an adaptive control could be achieved in the future if we can build a more accurate digital twin of job scheduling. Finally, I'll summarize this talk and then talk about our future challenges. Today, I have talked about our ongoing project to build a digital twin of a real-world HPC system. Toward building a digital twin, we developed a simulator to reproduce job scheduling of AOBA system. We extended the SLAM simulator and showed the feasibility of simulating job scheduling of the AOBA system. Using simulator, we also demonstrate that the simulation is helpful to do parameter survey and discuss the adequacy of the parameter configuration without actually changing the parameters of target HPC system in operation. In the future, we would like to further improve the accuracy of the simulator and utilize in the operation of AOBA. This concludes my presentation. Thank you for your kind attention.
Thank you very much. Are there any questions? I believe that we are all muted by default. So if you want to ask questions, just raise your hand. You can do it by clicking on the reactions. So does anyone have a question? When you, on the last slide, well, not on the last slide only, but you mentioned a Slurm simulator. It's the one simulator that actually uses the Slurm core, so it really allows you to try all the possible setups of Slurm, or is it just a name for your own simulator? If you know what I mean, like, is it the simulator that allows you to use a real Slurm to test things, or is it just a name of some simulator that you have built on your own?
Sorry.
Did you? Okay.
I am the co-author of this work. Can I answer the question?
Sure. Hello.
Yeah, actually, Slurm simulator uses the Slurm code.
Yeah.
So internally use Slurm implementation. So the Slurm simulator simulates the Slurm behavior. This is my understanding. Does this answer your question?
Yeah, because some resource managers have this mode of operation where you can you basically use the same the same scheduling system, exactly the same code as you would use in production, but instead you you somehow mimic the timing of job arrivals so that you can do it more quickly. So that was basically my question, because other simulators are really just simulating, but the code is totally different. So they can be much more faster typically, but it's not so reliable, because the implementation is basically different. So I believe that you're using the real Slurm simulator, which is somehow very close to the Slurm, at least according to my knowledge. But yeah.